Alright, last video on 3.3. This is the third part, final part. We're going to talk about something called the empirical rule and an idea called Chebyshev's inequality in this section. So the empirical rule, or some people call it the 68, 95, 99.7 rule, tells you if you have a bell-shaped data, or what a lot of people call the normal distribution, then roughly about 68% of your values fall within one standard deviation of the mean. 95% roughly falls between 2, and 99.7 roughly falls between 3. Alright, that's where it gets this other name from. And if you look at this is what we mean. If we have something that's bell-shaped, so we have a histogram, that histogram suggests a bell-shaped distribution, so we use this bell curve to represent the actual population of data. So if we have this mean right here in the middle, right, remember in a bell-shaped data, the mean is the same place as the mode, so it's right here at the peak. So up to one standard deviation above and down one standard deviation below, because of the symmetry in the bell curve, we roughly get a third of the data, or around 34% above and 34% below. Alright, and if we add those two 34% together, we get the 68 from the empirical rule. Alright, so again, if I was using the example from last time, if my mean were 100 and the standard deviation were 20, we'd add 20 and get to 120. We'd subtract 20 and get to 80, and we'd have a roughly 68% of our data falls between 80 and 120. If I were to sample continuously, I would note that of all the samples that I take, around 68% would fall between these two numbers. Alright, then if I go out a little further, 2 standard deviations above and 2 standard deviations below. So now I'm at 100 here in the middle, 120 above, and then 20 more above that would be 140, 80, 20 below, and then 20 more below would be 60. So roughly 68% falls here between 80 and 120, but the second part, the 95%, is between 60 and 140. So we went out a little bit further to the left and to the right, that same distance though, and we picked up a little bit more data. Alright, the bell curve is shrinking as we get further away from the mean, so we're not getting this same percentage again. Obviously we can, it would go over 100, but we're picking up more and more and more as we move our way out. We're picking up more area, right? It has to do with area, which we'll get into later. So according to the empirical rule and this made up data set that I have with a mean of 100 and a standard deviation of 20, roughly 95% falls between 60 and 140. Alright, and then the third part, the 99.7, if we go out a third deviation below and a third deviation above, then we get 99.7 of the data falls between those two numbers. Virtually everything. So that would be 120 for one deviation, 140, and then 160. Then below would be 80, 60, and 40. So if you have a normally distributed data set with a mean of 100, a standard deviation of 20, the empirical rule says that virtually all of your data is going to fall between 40 and 160. Virtually everything. Alright, and then we have 99.7% falls between there. So 0.3% falls on the outside. So this is actually should be about 0.15% falls above 160, and 0.15% falls below 40. Okay, that way these last two numbers add to 0.3, and then you add 0.3 to 99.7, you got 100%. So these are off just a little bit on those tail ends. Alright, but that's the idea here. If you notice, you can use these, pause this and write down these values in between. You can do a Google search for empirical rule and you can print off one of these as well. But these are the breakdowns of each one standard deviation at a time segment from left to right. If you just divide these distances up, you get these percentiles in each segment, or these percent values in each segment. Alright, so that's the empirical rule. Now we don't just always just go the same distance above and below. We can cut this up and do like 1 below and 2 above, or 3 below and 2 above, or some combination, and still get percentages. Alright, so we'll do that in some of the example videos I have in the next section below this, but this is what everything's based on. It's based on the symmetric properties and these 95, 99.7, and 68% values from the empirical rule that we're going to be able to do some of the other types of problems. Alright, and then Chebyshev's theorem, or Chebyshev's inequality, says that no matter what your data set looks like, whether it's bell curved or not, at least 1 minus 1 over k squared is the proportion of the values that fall within k standard deviations. So just so you can see where this is coming from, if k is equal to 2, I replace this k down here with 2, and I get k equals 1 minus 1 over 2 squared. Alright, 2 squared is 4, so that's 1 minus 1/4. 1 minus 1/4 is 3/4. Alright, and 3/4 is 75%. Alright, and that's where these values are coming from down here. So, no matter your data set, and I was alluding to this in the last video, 3/4 of your data falls within 2 standard deviations, or leaving only 25% to fall outside of that. Alright, and then if we extend that to 3 standard deviations, it goes to 8/9, or 89%, roughly 89%. So where does that come from? Well, same thing. Chebyshev's formula says 1 minus 1 over k squared, so that's 1 over 3 squared. 3 squared is 9, so 1 minus 1/9 is 8/9. Okay, and then 8/9, if you actually put it in your calculator, you get 0.8 repeating. So 0.888888 forever and ever and ever. And then to change that to a percent, move that decimal 2 places to the right. Slap on the percent sign. So we'd get 88.888888 forever and ever and ever percent. And so that's where the roughly 89% is coming from. Alright, so that's Chebyshev's inequality. Alright, it tells us a rough estimate of a lower bound of what percent of the data falls within whatever number you give it. Now when you do Chebyshev's inequality on your calculator, you just have to remember to put it in there in the correct order, which it really won't matter here. But 1 minus 1 over, in this case I did 3 squared. So I can just type it in exactly like that, hit enter, and it goes straight to the decimal. If you want it in fraction form, just hit math 1. That changes it to a fraction, and that's where the 8/9 is coming from. Alright, so you can plug it in there exactly in the formula and use your calculator to get the percentages if you want.